Hi everyone, this is Master, and today we're going to do some physics. It's project 1. My problem is number 3. I'm going to walk you through that. I'm going to remind you, if you like this video, smash that like button, subscribe for more epic physics and non-physics content, and let's dive right in. Alright, so problem number 3. A golfer hits a ball at a speed of 30 meters per second at an angle of 50 degrees above the horizontal and lands on the roof of a 11.5 meter tall building. Okay, so here it is sketched out. Velocity 30 meters per second, 50 degrees up, lands on the roof 11 and a half. Okay, so yeah, first question. How much time does the ball spend in the air before landing on the roof? Okay, so time before. Okay, so let's consider this situation. So we have velocity, right? Then acceleration due to gravity is pulling us down, and we land on the roof. Okay, so what defines time? What affects time? In this case, what we care about is the height, right? Because the horizontal doesn't have any accelerations, no forces, there's no friction in this question. So what we care about is the height. So if you imagine this pointer as the y projection of the ball, so it goes up, right? Apogee, then hits the 11.5. So we can find the time, using the good old displacement formula. So y is, the initial is 0 plus vertical. So we need the vertical component of this velocity. So it's going to be what? Sine 30 meters per second sine of 50 degrees. T. Now, downward acceleration minus g over 2 t squared. T squared. Okay, let's go and y is 11.5 meters. So let's sine 50 this by 30, 22.98, 22.98 t minus 4.9 t squared. If we rearrange this properly, it's 90 squared, 22.98 t plus 11.50. So good old quadratic equation. Let's go over here. Calculate. Okay, so we get two roots, this and this. Okay, so let's copy this. This is our T1. The second one is 4.12. Okay, so we have two roots, because parabola, right? At 11.5, we have two roots here and here, and we don't care about this one. We want the time when it lands, so it's the latter one, the bigger value. So for the first question, the answer is 4.12 seconds. Okay, sounds about right. Let's go to the next problem. How far horizontally from the golfer will the ball land? Okay, so now that we know the time it travels, we can just find the horizontal displacement. It's basic unaccelerated motion. Yeah, it's fairly simple. So the displacement will be initial 0, horizontal component of velocity, so cosine this time. 50 by 4.12 seconds. Okay, calculations. 50 cosine 34.12. 79.45. Let's do that. So 9.40. Was it 45? Yeah, 45. Meters. That's in meters. So number 3. Let's see. What's the ball's maximum height above the ground? This is a bit more interesting because we want this maxima, right, when it's highest, and we want the exact height from here. Yeah, so to do that, what exactly is this maxima? It's basically when the derivative of this trajectory is 0, so when the vertical component of velocity is 0, right? Acceleration is still downwards, but it's 0 here, then it goes down. We can use the velocity squared formula for this. 2, y is initial squared minus 2 accelerations, in this case g, and displacement. So why we're using this formula? Because we know the velocity we're looking for is 0 at the height, apogee. So this, the initial one, vertical component, 30 sine, we already found that, 50, this thing squared, minus 2 g's, and the delta, the actual height we're looking for, so it's going to be this thing squared over this. Let's go to calculator. Squared divided by 2 g's, 2.8, so it should be 26.95 meters. Yeah, 26.95 meters above. This thing is supposed to be this, 26.95. Okay, yeah, sounds reasonable. About more than twice, right? Okay, let's move on to the next question. Okay, so number 4. Okay, so how long does it take the ball to reach? Yeah, how long does it take to reach this? The time it takes. So for that, we can use the normal velocity formula with acceleration. Initial minus gt, right? We know this thing to be 0 because the maximum, right? So we know the y component, this one. And t we need to find minus 9.8 t. So t is going to be, what is it? This thing, was it 22 and 8? 9.8 meters per second squared. This is meters per second. Get 2.35, right? 2.35 seconds. Okay, so that's that for number 4. Next, with what velocity, magnitude, and direction will the ball hit the roof? So yeah, we need the velocity, magnitude, and direction right here. Okay, it's doable. Basically, it's we'll need to find it separately for y component and x component, and then do the hypotenuse thing and direction with the inverse tangent. Yeah, let's do that. Okay, so separately, y component and x component. So to find the x component velocity, the initial, that's just it. It's the initial, the x component is the same throughout. Was it 19.28 meters per second? I think so. But the vertical, as we already know, is the one that changes due to gravity. So the initial y component, it's this one, 22.98. That minus g. So it's this one, but since we know the time when it hits the roof, remember it's 4.12, we can find the velocity at 4.12. So it's going to be the 2290, 2289, no, sorry, 98 meters per second, minus g 9.8 bar 4.12 seconds. Remember from the first question. Okay, if we do some magical calculations, it's going to be, since I already have the answer, 4.12, negative 17.4. 17.4 meters per second. Okay, sounds reasonable, because we gain acceleration, right? But it's still less than in the beginning, because we didn't reach the end, so it's a bit, the magnitude is less than here. Yeah, sounds right, negative 17.4. Okay, so we know those values separately. Now we can do the hypotenuse, the big square, to find the magnitude. X squared plus squared. Yeah, 1928. And negative 17.4 squared. With the magic of editing and calculators, we get, okay, so it's this, square root 2597 meters per second. Yeah, magnitude 2597 meters per second. Okay, so that's the magnitude. Now we need the direction. Yeah, that we need to use tan inverse. So theta is tan inverse of the vertical component over x. Tan inverse of 17.4, 17.28. So let's use the arctan calculator. 17.4 for 1928. It's negative, so this thing to the arctan. Negative 42, this is in degrees, roughly 42.1, so around here, more than that, yeah, at 42. Yeah, sounds good. Sounds good. It's still less than 50, because remember, if it didn't land on the roof but on over here, it'll have to be 50. But it landed earlier, so the angle is a bit smaller. So 42.1 degrees below horizontal sounds about right. 42.1 degrees. Yes, so that's the this is magnitude and this is direction. This is below the axis. Okay, so that's it for the calculations. I think I got them right. We can go ahead and go over to the coding part, make the simulation of this movement, and see you there. Thanks. This was Master. Okay, and we're in GlowScript. Here's the same simulation that we had over there. Golf ball trajectory, 11.5 meter tall building. Yeah, it looks pretty accurate to the sketch, actually. Yeah. Okay, let's look at the code. So here we have the ground, basically a thin green plane. The building is just a box which is elevated just enough so that this height is fully there. See here, 11.5. So we have three moving objects, basically the ball itself, two vectors, velocity and acceleration. Initially, the velocity is 0, they just at rest, but they'll start moving when we click. Here, wait for a click. So in the beginning it's all 0, and I assign velocity value here, not to overcomplicate this line, because we need trigonometry here. Basically it's 30 meters per second, right? Cosine of the 50 degrees in radians, of course. So we convert them. And I didn't put velocity as an attribute of the ball, just put it separately. First of all, because there's no reason, there are no special methods for it, but this way it's easier, just velocity. And I won't need to write ball dot velocity, it's just velocity is a separate variable, of course a vector. Then we have the time, which is just a counter, going to see a track time of different events. We're going to use this universal variable of time. Now here's the dt, and it's related to animation. This is a small change in time which will over which all these transformations in velocity position happen, right? And it's connected to the rate thing, because we can make it just 1, and update it every second and make the rate 1, and it mathematically works, but it's very slow and it's imprecise, not consistent. So not consistent with calculations. So we have to make it a bit more smooth, and make the dt a bit smaller and the rate faster so it updates quicker. And if we do everything right, this shouldn't be affecting math, because there's a mini change in time, and all the velocity and position change the same amount, but it happens that much faster. So there shouldn't be any differences in calculation as soon as we change them inverse proportionally, right? So that's that about dt and animation. Now the acceleration, it's only due to gravity. We don't have friction, we don't have horizontal forces, nothing, just minus 9.8. Now another vector here, the acceleration vector, remember here everything was 0, and here we assign it the value of a, right? But not just a, it's a by 3, and here also velocity, also a by velocity over 3. There's no particular reason, it's just to make it smaller and make it like adequate looking so it fits the picture here. See, without the dividing by 3, it would be a huge arrows, and we don't want that. So it's just divided by 3, not to scale, but whatever. And here we just wait for the click before starting the actual movement, for the golfer to hit, so to speak. So the while loop, I didn't make it just true for it to keep going until something and make it some if statement. I just put while the ball, primarily this, while it's above 11.5, so that when it hits 11.5 it stops. But because in the beginning it's also less than 11.5, we need another condition that x component is less than 10, basically. Without that, it would just stay there because it's less than 11. But we add another condition that if it's less than around here, less than 10, it should still keep going. So hopefully that it only stops over here. It's basically the conditions. So the rate 100 related to dt, remember? And here's the movement physics part. We change the vector, like for the location of the ball, based on velocity over this small increment of time, right? Then we add this new vector to the previous position. So this is basically a small change. Basically, this is small displacement, over this small time. And we add that displacement to the position. So basically every update of the loop is the ball moving slowly. Because remember, these values, velocity, acceleration, position, they aren't like ultimately smooth, and it's perfect and everything is continuous. This isn't actually continuous, it's just a bunch of iterating pictures, you know? So everything at the end depends on this. Everything affects this. So velocity affects dr, then acceleration affects velocity. But at the end, everything is just, you know, continuous movement of these pictures, you know, over and over, dr. I hope you understand what I mean. And here we add to the position, right? So here's the velocity vector. Remember the arrow? This one. This arrow. Here we add the same differences, because remember the position of the ball and position of these vectors is the same position. So they both change at the same time. We assign the same dr here and here. Now the velocity vector, of course, divided by 3 because it's too long, you know. And here we increment our velocity based on a. Remember? Here. Change it with dt by a. And here we're just adding dt to our time, basically our time of the event. So later we can print out here. That's basically the code. Now, I guess we can just watch it properly. Here we have the a is just there because the acceleration is always there, so it doesn't depend on the click. But when we do click, you can see this. Nice, beautiful. And yes, well, basically it starts moving right away, you know, just instantaneous acceleration. But that's not the point. It's more about the trajectory and that sort of stuff. So we have the constant acceleration down, and the vector changes. Here it's 0, remember, apogee, and then it hits 11.5. So what are the questions? Yep. So you saw the vectors, trajectory. Now we can use this simulation to find the questions from part A to match to this stuff. Remember? So the first question was about time, how much time did the ball spend in the air? So for that, remember this universal time thing? We could just print it out at the end. We can print time and this t after it looped, after it stopped at the roof, you know. So time 4.14, and here we have 4.12. Well, yeah, it's not radically different. It's basically, yeah, it means we got it right. Just some uncertainty, which we can fix later by making it higher refresh rate, you know, and hopefully there are less imprecisions. Next question, how far horizontally? Yeah, it's also very easy because we know the initial location here, remember, minus 50, and whatever change we have, we can just add 50 to that. Here, x displacement. Whatever the position is of the ball, just add 50, and we get the displacement from that point. X displacement 79.84, 83. 9.83. Yes, right here. But here it's 79.45. So as far as that goes, yeah, it's pretty close enough. The ball's maximum height. Oh, this is again more interesting because basically what we can do is as soon as the vertical velocity is 0, we can make an if statement, put it there, and when it is 0 or close to that, it can just print out the height. You know? So what we can do is just add an if statement like this in the loop. If the velocity, we can't just put 0 because look what happens. If we just put, if this thing is 0, if we do that, nothing happens because the value of y probably doesn't even get to 0. These iterations, they aren't perfectly continuous, you know, so it just skips v equals 0. So what we can do is we'll have to widen this gap a bit so that it includes more than just 0. Hopefully we can catch a few instances where it is roughly up there. So negative 0.1 to 0.1. Let's see if there are any matches. Yeah, it catches 2 situations right there. The first here, pretty similar. Max height 27.06. Yeah, it's the same. And time is also pretty similar. It's just 2 points which were the closest to apogee. And time is 26:45. 20, and here it's 27. Close enough. Also, we didn't get anything radically wrong. It's probably just because the uncertainty. So the physics and math part is right. Likely. Next question. How long does it take? Yeah, so as soon as this thing triggers, you can just print out time 2. You know? Let's put an extra line here so it's visible. Yeah, time, as we saw, and comparing it to the calculations, the time is, in calculations it's 2.35. Here it's the latter one is 2.35, close to that. The other ones aren't that accurate, but still good. Now, 5/5 with what velocity? Okay, this is a lot of math, so it's interesting. Let's do that. Basically what we need is, okay, so we know the x component and y component. We printed it out. The y is this, negative 17.59, and this is the x component. And if we compare it to the calculations from part 5, if you remember, yeah, the x one was 19.28. Here it's actually accurate, 19.28, and y negative 17.4. Yeah, close enough. What now we have to do is do some triangle math and get the magnitude. We can make a little function here, hypotenuse, just to make our life a bit easier. Here, just a function that you input x and y, and it gives you the hypotenuse. And what we can do is just print it out, velocity magnitude, right after this. And that function, let's input the x and y component, right? This should output the magnitude. Yeah. And magnitude is 26.1. See here, square root. It's 25. Yeah, it's almost 26. So yeah, again, it's pretty close. Nice. Yeah, in direction. So for that we need some inverse tangent. So we can just add it here. So yeah, I think it's A10, right? And A10 we put the ratio of y component or x, and this should give us the ratio of the angle we're looking for. Arctan will give us the angle in what, in radians. It might give it in radians, so what we need to do is do this. Whoops. Let's see if it works. Yeah, negative 42 point, and here it was negative 42.1. Negative 40. Yeah, good, nice. So overall we have like maybe a couple tenths of imprecisions, but overall all the answers match our calculations. Nice, and it looks cool too. It's now we can make it a bit more precise by making the animation a bit quicker, so might as well do that and see what happens if we get closer results to the calculations. If we make the change in time even smaller and the refresh rate. Add a couple of zeros over there. Oh, too many zeros. Sorry. Yep. It's a bit smoother. And if you noticed, we got way more values here of the apogee because the window that we left there was so big that there were so many versions. So let's make this too a bit more precise. Let's add a bunch of zeros. See what happens. Oh yeah, and we get just two values which are closer now. So 26.947 max height. Yeah, 26.45. So cool, amazing, very precise. And displacement is 79.46 now, just like here almost. And everything else, time 4.12, magnitude 25.97. See 97. An angle 42.06. Remember if we round it here. Okay, great, looks great. It matches. If we do it faster, if we refresh it faster, then we get more precise answers. And it's nice. Golf trajectory. Nice. So this was Master. We did some physics, project number 3. We answered some questions, ran a simulation. If you like this video, smash that like button, subscribe to the channel. Good luck with your physics education, get that degree and have some fun. Yeah, tune in for more videos later. See ya. Thanks. I should have gone to computer science.